Mart van Baalen, who's the Chief Staff Engineer Manager from Qualcomm AI Research in Amsterdam. His work focuses on efficient deep learning inference, primarily through neural network quantization, as well as other methods to maximally exploit efficient inference hardware. Mart joined Qualcomm in 2017 as part of the acquisition of a UVA spin-off Cypher. Beside his work in AI research, Mart is a professional trombone player. Yeah. Thank you, Mart.
Thank you. Hi, my name is Mart. I'm a staff engineer at Qualcomm AI Research in Amsterdam, and today I will present about advances in quantization for efficient on-device inference. And this presentation will consist of two parts. In the first part, I will discuss two low-bit numerical formats and compare their benefits and drawbacks. And in the second part, I will introduce two methods to address challenges our lab encountered in low-bit quantization. So the last few years have shown incredibly exciting new capabilities in neural networks that I'm sure you are all aware of. So we've seen Stable Diffusion recently, ChatGPT, many applications of large language models. But these capabilities come at the cost of exponentially increasing neural network sizes, as we see in this graph here. And obviously, these large models pose challenges in terms of power consumption and latency, especially when running on edge devices. Oh, sorry. Yeah, I got to press this one as well. I'm sorry. Yeah, thank you. So this was the graph I was talking about. I'm sure you've seen many like anyway. So let's zoom a bit on what globally happens in a deep learning accelerating during a forward pass at inference time. First, weight and activation tensors are transferred from memory to the compute engine. Individual weights and activations are multiplied and added together in the accumulator. And after this, a nonlinearity is applied, and the activations are written back to memory. So each of these steps comes at a cost of power and latency. So it costs a little bit of energy and it costs a little bit of time to perform each of these steps. And besides this, fast compute engines take up area on a chip, and this area is extremely expensive. So the smaller we can get this, the better. And the most powerful tool that we have to combat these costs is weight and activation quantization. So here we reduce the number of bits required to represent weights and activations in order to reduce the power and latency required to perform a forward pass. And this reduces cost every step of the way. So we get lower latency because we can use lower precision in multiplication and accumulators. And we need to transfer less data. We have lower power consumption for pretty much the same reasons. And we can use less die area, less chip area for our compute engine because we don't need as many two-input gates for our lower precision multipliers and accumulators. And this leads to cheaper chips. So low precision formats provide mitigations across the line for neural network inference. But which number format should we use? In this presentation, we will compare INT8 and FP8, as these are the two most common low-bit number formats, both being currently implemented in commercially available hardware. And we will now proceed with comparing these formats closely on two axes. Hardware implications, so what does it take to actually implement these formats in hardware? And accuracy implications. What happens to the accuracy of a model if we want to run inference in INT8 or FP8. First, we provide a quick overview of how INT8 and FP8 number formats differ. INT8 and FP8 have the same number of values, but for INT8, these are spread evenly between a minimum and a maximum value. And for FP8, these values are more concentrated near 0, whereas they're more spread out as you move away from 0, as you can see in this figure here. And the result is that FP8 is better at representing outliers, or representing distributions with outliers than INT8. Under the hood, FP8 formats consist of a sign bit, a number of mantissa bits, and a number of exponent bits. Through the division between the exponent and mantissa bits, FP8 formats can trade precision for dynamic range. And this means that the more exponent bits we have, the larger the dynamic range, but this comes at the cost of reduced precision. The FP8 formats most commonly proposed in the industry are FP8 with 4 exponent bits and FP8 with 5 exponent bits. FP8 with 4 exponent bits mostly for inference and 5 exponent bits mostly for gradients. And we refer to these as FP8E4 and FP8E5. So in this talk, we will mostly focus on FP8 with 4 exponent bits, which we refer to as FP8E4. The question then is, how do these formats compare? from a hardware and an accuracy perspective. First, let's discuss what a realistic hardware application, implementation of each format would entail. While we can provide precise power, latency, and area measurements directly without building a reference implementation, or at least a simulation of it, we know that 2-input gate count correlates pretty well with these metrics. So here we compare the number of 2-input gates required for different types of accumulators for INT8 and the FP8 format. And for the accumulators, we compare Coolidge-like fixed-point accumulators, which are exact, to 16-bit and 32-bit floating-point accumulators, which are inexact, as floating point is, but more efficient for floating-point formats with more exponent bits, so FP8 E4. And in this table, we can see how many 2-input gates are required for each combination of input format and accumulator. And we see that a fixed-point accumulator for FP8 with 4 exponent bits requires 52% more 2-input gates than a fixed-point accumulator for INT8. Furthermore, we see that while an FP32 accumulator is more efficient for FP8 than for INT8, it still requires, that an FP32 accumulator is more efficient for FP8 than a fixed-point accumulator. It still requires 183% more 2-input gates than INT8 with a fixed-point accumulator. So in conclusion, accumulators for FP8 are 53% to 183% less efficient than for INT8. But what about accuracy? Does FP8's ability to represent outliers translate to better accuracy on a variety of tasks? Before we dive into model results, we first present some more general results on using INT8 and FP8 formats to quantize various distributions. We first investigate how well INT8 and FP8 can quantize probability distributions that correspond to weight distributions commonly found in neural networks. And we do this by measuring signal-to-noise ratio, where higher is better. And we find that INT8 is best at quantizing uniform distributions. This is not a surprising result, I'm sure. And FP8, as we predicted, is better at quantizing distributions that have outliers. So here we see a normal distribution and a student t distribution. However, FP8 with 4 exponent bits only performs best on a student t distribution with very large outliers. Whereas normal distributions is quantized best with an FP8 distribution with 2 exponent bits. And these results are in line with what we saw before. The bigger the outliers, the more exponent bits we need. So let's turn to model results. For post-training quantization, the best format is often FP8 with few exponent bits, as we can see in this table. And this is because weights in trained neural networks often correspond to scaled normal distributions. And we saw in the previous slide that this is best with few exponent bits. FP8 with 4 exponent bits is only best for BERT on glue, and this is due to the large activation outliers that we often see in transformers. And we will talk a bit more about this later. For quantization-aware training, the gap closes. So here, INT8 is always the best or competitive, whereas FP8 E4 is never the sole best format. There's always competition from FP8 E3 and also from INT8. In our white paper, FP8 versus INT8 for efficient deep learning and the associated NeurIPS paper, we provide many more results. So let's recap. FP8 is less efficient in hardware. Post-training quantization performance is sometimes better in FP8. But in PTQ, no FP8 format consistently outperforms all others, which is specifically the case for FP8 E4, which is currently considered in the industry. After QAT, INT8 often gives better accuracy and is always competitive. So in conclusion, for on-device inference, INT8 provides most benefits. So this brings us to the second part of our presentation. Since we've established that integer quantization has many beneficial properties for inference, I'd like to highlight a few challenges in integer quantization that our lab has recently addressed. First, we will talk about oscillations in quantization. We wrote a paper about this that was accepted to ICML in 2022. And next, we will talk about outliers in large language models, which is currently under review but available in archive. So first, overcoming oscillations. Before we dive into oscillations, I would like to give a short recap of quantization-aware training. To let a neural network model adapt to quantization noise on weights and activations, we train the neural network with quantization simulation. And for this, we add quantizer objects. these discretize the weights and activations during training. So during a forward pass, they're passed to the quantizer, and we use the discretized versions in our forward pass. However, the rounding operation is non-differentiable. So to still allow optimization with gradient descent, the gradient is commonly approximated with the straight-through estimator, or one of its variants. So this just assumes that the gradient, that this not the step function is just a linear function, as you can see in this plot right here. It's important to note that during QAT, during and after QAT, the high precision weights are by themselves meaningless before quantization is applied. They should be seen as gradient accumulators rather than higher precision version of the quantized weights. And to illustrate this, let's look at a simple quantized regression problem. We have one latent weight W, we have a quantized weight Q of W, and we optimize a least squared objective with a target value of W star. On the right, we see what happens during the optimization with gradient descent. We see in the blue line, there it is. In the blue line, we see the value of W, so this is our high precision weight. The green X's show the value of the quantized weight. The target value is the black dashed line, and the red dotted line is the decision threshold. So above this line, we round up, and below this line, we round down. And as we can see, the latent weight starts approaching the optimal value, but then continues to the decision threshold and starts oscillating around it. And to understand why this happens, let's look at the gradient. The gradient of the rounding operation in most places is undefined, and therefore frequently approximated with the straight-through estimator. This results in that the gradient is proportional to the distance of the target value to the quantized value. And we can see that this leads to having a small gradient until we reach the decision threshold, and then the sign flips, and we have a stronger gradient in the opposite direction. So the gradient approximation in the straight-through estimator is what causes the oscillations in quantization-aware-training. In our paper, we introduced two methods to mitigate the problem of oscillations. We introduced dampening. In this method, we add a regularization loss term to the objective, which penalizes weights that deviate too far from the quantization bin center. This is on the left. Oh, here's the button. And iterative weight freezing. In this method, we track an exponential moving average of the oscillation frequency of a weight and freeze it if this exceeds a certain threshold. And these fix the QAT issues, as we will show in this slide. So here we present the results of our methods on training quantized MobileNet v2 and compare it to competing QAT methods in the literature. And we achieved state-of-the-art results for 4 and 3-bit weight and activation quantization. Specifically for 4 bits, we improve over the strong LSQ baseline by 1%. And we also marginally outperform the recently suggested EWGS and bin regularization methods. That's this one. For 3 bits, we improve even further with over 2% compared to LSQ, and for 0.4% increase against bin regularization. So it is worth noting that despite both dampening and freezing performing on par with each other, iterative weight freezing is 30% faster than dampening during training. And we provide many more results in our ICML paper. Sorry, I will just go back. Show that for 1 second in case anyone wants to take a picture. Okay. Next, we will discuss outliers and transformers. So transformers tend to learn big outliers. We've observed this before, and others have observed this as well. There's several papers that have remarked on this. And these outliers make transformers hard to quantize to 8-bit fixed point after training. These outliers mostly occur in the residual addition after the FFN block, while within a transformer block, marked in red in the picture on the right. So that's this thing over here. That's where we see most of the outliers. So why do these outliers occur? Our hypothesis is that transformers want to be able to pass a stroke straight through. So that means not providing an update. So, struggling with this thing. So we want to follow this path, and we want this one to be 0. But this requires zeros in the attention, which requires large values in the input to the softmax. However, the layer norm in the previous layer normalizes outliers. which mean that the FFN needs to produce very, very large values, because after normalization, these will shrink. And since softmax doesn't saturate, gradients will always increase the value. So again, we introduced two methods to mitigate the problem of oscillations. The first method is called clip softmax. So if a softmax probability reaches a certain threshold, we clip it to exact 0 or 1 and apply additional normalization. This means that the input to the softmax does not need to approach positive or negative infinity to ensure the softmax value approaches 0 or 1. Instead, the clipping ensures that the gradient to the corresponding activation is killed when the threshold is reached. The second method we introduce is attention gating. Here we introduce a gating mechanism that turns off certain tokens. The gating mechanism is a small neural network that takes the same embeddings as input as the attention mechanism. And the idea behind this is that by allowing the gate to turn off certain tokens, the activations don't need to saturate the softmax. So they, again, don't need to grow to positive or negative infinity. And we show here that both approaches significantly dampen outliers and make 8-bit integer post-training quantization possible. We compare BERT, OPT, and VIT with regular FP16 or FP32 training to training with our method applied. First, we see that high precision accuracy is not harmed by our method. In fact, it is sometimes actually improves a little bit over the baseline. Second, we see that outliers are significantly dampened. So here, for example, we see that the largest value in the activations goes down from 735, which is hard to quantize, to 21.5. And lastly, as a result of this, in the last column, we find that our networks are a lot easier to quantize than networks trained in the normal way. And we see that in all cases, the INT8 PTQ model is actually very close to the original model accuracy. Our paper has many more details and results, and I would invite you to read it. So a few concluding remarks. INT8 is great, and there are still challenges to tackle for us and for other researchers and for the community in targeting lower bit widths in the future. And with that, thank you.
Thank you very much, Mart.